6.4 goes over exponential growth and decay. We're going to first look at exponential growth. We're going to be using the formula that you see here, that y is equal to a times 1 plus r to the power of t. Your a is your initial amount, so anything that is deposited into an account or that you're starting with is that a value. The r is going to be your rate of growth in decimal form, so whatever percentage they give you, you're going to turn into a decimal and put it in for r. And then your time is put in as the exponent, and your time is always in the form of years. So if it's 6 months, that's 6 months out of 12, which is 1/2. That would be your power, is that 1/2. If we look at example 1, it tells us that the inaugural attendance of an annual music festival is 150,000. The attendance y increases 8% each year. A asks us to write an exponential growth function that represents the attendance after t years. So to get this with our formula that they gave us, that y is equal to a times 1 plus r to the power of t. What I like to do is I like to identify all my variables first. My y is going to stay y unless it gives me that ending amount. So my a is that starting amount. My a, they told us that we had 150,000. The r is your rate, which is expressed as 8%. So we have to turn that into a decimal. Remember, turning a percent into a decimal, you're moving the decimal point 2 places to the left. So this would be 0.08. From here, we're representing it with the amount of t years. So t is going to stay t for right now. So if we plug these values in, this is going to give us y is equal to 150,000 times 1 plus 0.08 to the power of t. B asks us how many people will attend the festival in the 5th year. Round your answer to the nearest 1,000. Now, with this, the only thing I'm going to ask you to do is to plug in the power for time and simplify what's inside the parentheses. You're not going to be solving it completely because you're not working with calculators. So if you were working with calculators, I would expect you to simplify it fully. However, you're not. So what you're going to do is you're going to take this formula, this y is equal to 150,000 times 1 plus 0.08 to the power of t. It told us the 5th year, so t is going to equal 5. From here, you're just going to simplify what's inside the parentheses. So you're going to be ending with y is equal to 150,000 times 1.08 to the power of 5. I don't expect you to sit there and waste time going 1.08 times 1.08 is what? Then multiply that by 1.08. Then whatever you get from there, multiply it by 1.08. Then whatever you get from there, multiply it by 1.08. And then multiply that by 150,000. I'm not doing that to you. Okay? So this is as far as I'd like you to go with these types of questions. For example B, it tells us that a website has 500,000 members in 2010. The number y of members increases by 15% each year. We need to write an exponential growth function that represents the website membership t years after 2010. And then it asks how many members will be there in 2016. So using all of this, our initial amount is that a value, which is 500,000. Then it tells us that our rate, it goes up by 15% each year. So as a decimal, that's 0.15. It wants to know in the year 2016, so our t is going to equal that 2016 minus 2010, because that's where we started at. So that's going to be 6. So we plug all this into our formula. Remember, our formula is y is equal to a times 1 plus r to the power of t. So this is going to give us y is equal to 500,000 times 1 plus 0.15 to the power of 6. We have to simplify inside those parentheses and then we'll be done with this one. So ultimately, we're going to have y is equal to 500,000 times 1.15 to the power of 6. If we look at our next part, we're working on exponential decay with this. So instead of adding that 1 plus our rate, we would subtract that rate from 1 when we're working with decays. If we look at our second set of examples, we're just identifying whether or not we have exponential growth or decays. With these, if you're a constant rate with your y, so that change with your y is being multiplied by a whole number, you have a growth. If it's multiplied by a fraction that's less than 1, you have a decay. So if we look at example A, those values that we have for our x's are 0, 1, 2, and 3. These are all going up by 1. So we know that those are constant. Forget about those. Work with your y values. From 270 to 90, we're multiplying this by 1/3. From 90 to 30, we multiply by 1/3. From 30 to 10, we multiply by 1/3. So this, because you're multiplying by a fraction that's less than 1, is a decay. Example B, we're given x values of 0, 1, 2, and 3. So again, these are going up by 1s. We have a constant rate here. Move on to your y values. Forget about your x values. From 5 to 10, you can add 5. You can also multiply by 2. From 10 to 20, you can't add 5. So we have to go with that multiply by 2 because 10 times 2 is also 20. From 20 to 40, we multiply by 2. So your constant rate here is being multiplied by 2. So this one is a growth. For example C, we have x values of 0, 1, 2, and 3. So again, these are all going up by 1. Move on to your y values. From 64 to 16, we multiply by 1/4. From 16 to 4, we multiply by 1/4. From 4 to 1, we multiply by 1/4. So you have a constant rate here that's being multiplied by 1/4. That 1/4 is less than 1, so we have a decay. For example D, from 1 to 3, you're going up by 2. From 3 to 5, you go up by 2. From 5 to 7, you go up by 2. For your y values, from 4 to 11, you can add 7. From 11 to 18, you can add 7. From 18 to 25, you can add 7. So, is this exponential at all? No, it's not. You have a constant rate of change with your x and your y values, yes, but the change in y over the change in x is representing a linear function because it's done with addition. So this is not exponential at all, so you would just give that it's neither. For our next part, we're determining whether each function represents an exponential growth or exponential decay and identifying the percent of change. With these, the number that's in the parentheses that's being raised to the power of your time tells you whether or not you have a growth or decay. If it's greater than 1, you have a growth. If it's less than 1, it's a decay. If we look at example A, you have y is equal to 5 times 1.07 to the power of t. So what's the number inside the parentheses that the t is being raised to? That 1.07. 1.07 is greater than 1, so we have a growth. What is the rate of that growth? Well, in order to find what the decimal was that you added to 1 to get 1.07, we can just subtract 1 from this. We get 0.07, and we would turn that into a decimal. So we can move that decimal point 2 places to the right, and that's 7%. So we have a growth of 7% here. So in example B, they give us f of t is equal to 0.2 times 0.98 to the power of t. That 0.98 is what's in parentheses that's being raised to the power of t, and 0.98 is less than 1. So since it's less than 1, we have a decay. To find what our percent was of that decay, because the number is less than 1, we're going to take 1 and subtract the number inside the parentheses from 1. So 1 minus 0.98 will give us the decimal form of the percentage that we're decreasing by. If we turn this into all of the numbers we need to, we get 0.02. We move that decimal point 2 places to the right, so that's 2%. So we have a decay of 2% for this one. For C, we have y is equal to 2 times 0.92 to the power of t. So that number that's inside the parentheses that's being raised to the power of t is less than 1. So this is going to be a decay. Next, we find the percent. So we're going to take 1 and subtract 0.92 from 1. This 0 turns into a 10, this one becomes a 9, this one becomes a 0, so that's 0.08. We turn this into a percent, we move that decimal point 2 places to the right, we have 8%. So that's a decay of 8% each year. For example D, we have f of t is equal to 1.2 to the power of t. Now this is not in parentheses because there was not a term in front of the original parentheses on this 1.2. So this is the same exact thing as seeing f of t is equal to parentheses 1.2 to the power of t. So if it makes it a little bit easier, just rewrite it so that way you can see it in that form. That 1.2 is greater than 1, so we do have a growth. In order to find that growth, we're going to do 1.0 or 1.00 minus 1.2 minus 1.0. This gives us 0.2. We move the decimal point 2 places to the right, add in that 0, so that's 20%. So we have a growth of 20% each year. Your next part of this lesson goes over rewriting exponential functions. When we left off at example 4. With example 4, it just tells us to rewrite each function to determine whether it represents exponential growth or exponential decay. So we're just rewriting these to see like where that like percent would be plugged in for those equations. So if we look at example A, it gives us y is equal to 100 times 0.96 to the power of t over 4. Don't worry about this t over 4 as your power. The whole thing that you want to do is look at the term that's inside the parentheses that t over 4 is being raised to. So with this number is that 0.96. So that 0.96, again, is less than 1. So this is going to be a decay. So with these, the only thing that I need you to give are whether or not it's a growth or decay. I don't really care about the actual equation. I don't care about the formula. I don't care about the percentage. I care about whether or not it's a growth or decay. For example B, we have f of t is equal to 1.1 to the power of t minus 5. Again, we're not worrying about that t minus 5. The only thing we're worrying about is that number that's inside the parentheses. So that 1.1 is greater than 1. So this gives us that it's a growth. For example C, we have f of t is equal to 3 times 1.02 to the power of 10t. So that number that's inside the parentheses that's being raised to your time is that 1.02. 1.02 is greater than 1, so this one is a growth. For example D, we have y is equal to 0.95 to the power of t times, t plus 2. So that number that's being raised to the power is that 0.95. 0.95 is less than 1, so we have a decay with this one. The next part of your lesson goes over compound interest. Your compound interest formula is a little different than your formulas that you've used for your exponential growth and your exponential decay. Your compound interest formula is y is equal to p, which is your principal, that starting amount, times 1 plus your rate as a decimal over the number of times it's compounded per year, all raised to the power of the number of times it's compounded per year times your time. So if you looked at these questions that we just did with the part that it's in example 4, all of those exponents were similar to this, because those different functions that were given to you, some of them were compounded interest functions. So with these, the only thing that I'm going to ask you to do is to set up the formula. You're not solving them, you're just setting up the formula. Okay, so if we look at example A, it tells us that we deposit $100 in a savings account that earns 6% annual interest compounded monthly. Write a function that represents the balance after t years. So you got a couple things you got to pull apart here. It tells us that we deposit $100. If we deposit $100, that's our initial starting amount. So that's what P is. So P is $100. The savings account earns 6% annual interest. So your rate is 6%. So as a decimal, that's 0.06. Because remember, we moved the decimal point 2 places to the left to give us that decimal form of the percent. Now, it tells us that it's compounded monthly. So n within this formula is the number of times interest is compounded per year. So if it's compounded monthly, how many months are in a year? 12. So our n is 12. And lastly, you would find your t, which in this case we're not given, so we're going to leave it as t. The only thing we're going to do is plug in these values into that equation that was given to us for our compound interest, which is y is equal to p times 1 plus our rate over n to the power of n times t. So if we plug all these values in, we're going to have y is equal to 100 times 1 plus our rate, which is 0.06, over n, which is 12, raised to the power of 12t. Now with this one, you could simplify it inside those parentheses, but I'm not going to require you to do so. So we can leave it just like this. So we can see that our starting amount is that 100, our rate is the 6%, and it's compounded monthly because that 12, that's in the denominator of that fraction, and that's being multiplied by t. So if we look at example B, it tells us that we deposit $500 in a savings account that earns 9% annual interest compounded monthly. Write and graph a function that represents the balance y in years after t years. I just want you to write the function, that's all. So pick out your A, pick out your R, pick out your N. So A is our starting amount, which in this case, we deposit the $500, so we start with 500. Our rate, it tells us, is 9%, which gives us a decimal of 0.09. Then our n is the number of times it's compounded yearly. This tells us that it's compounded monthly, so how many months are in a year? 12, so n is 12. If we plug this into our formula is y is equal to p, in this case it's p, not a, I'm sorry. This is supposed to be p. Y is equal to p times 1 plus our rate divided by n raised to the power of n times t. So y is equal to, we said p was 500, times 1 plus our rate as a decimal, so 0.09, divided by n, which is 12, raised to the power of 12 times t.